So welcome to the second video of the Unit 4 playlist over Electron Configurations. We're going to be learning how to give an address to each electron by doing what are called electron configurations. So first let's go over a couple of rules. So there are 3 rules of electron configurations. I have 2 of them on this slide. The first one is the off-ball principle. Basically, it states that you have to fill orbitals starting at the lowest energy level and then work your way up to the highest. You will display the off-ball principle every single time you do an electron configurations, and I'll teach you how you do that in our first example. The next rule is the Pauli exclusion principle, which is just kind of common sense. It basically says that electrons can only be in one place at a time. Electrons can move from certain energy levels and then back down, but they can only be in one place at one time, which is kind of common sense. The last rule is called Hund's rule. Basically, it says you have to fill orbitals of equal energy first before you pair them up. We don't do Hund's rule until we do orbital diagrams. And so you won't see this rule except for whenever I ask you to do an orbital diagram. So I will explain what exactly this rule means whenever we work out our example. Okay, so you are going to get this reference sheet tomorrow. This is basically how you write an electron configuration. So there are 3 parts. The very first part is the number in the very front. For example, this is a 1. The number in the front corresponds to the row number or the energy level. Remember that we have 7 rows and there are 7 energy levels. You can also call an energy level a shell, but this is an old term that we don't use very often anymore. So the first number you just get from the row. Then the middle part, the letter, corresponds to the orbital. We learned last week that there are 4 different orbitals and they are based on a letter. And remember, the only thing that's different between each one is their shape. So we have the S, P, D, and F orbital. These are also called subshells, but we don't use that term very much. So I will teach you how you know what orbital you're going to be placing an electron in just by looking at the periodic table on the next slide. And then the very last component, it is a little number up high and to the right. This number corresponds to the number of electrons that you have placed in that orbital. So remember, I made you guys write this down. The S orbital can only have up to 2, P can only have up to 6, D can have 10, and F can have up to 14. Whenever you're writing these electron configurations, one way you can check your work is by adding up all of these little bitty numbers here. And that should equal the total number of electrons that an atom has, which should be equal to its atomic number, because that is what it'll be if it's neutral. So let's look at how you can use a periodic table to write these. So this is the periodic table that you are going to get in class tomorrow. This is a periodic table that will help you figure out how to write the electron configurations, because it is labeled in what are called blocks. Each block represents a different orbital. So the very first 2 columns is the S block. Then we've got the very middle block where the transition metals are found in the D block. And then the P block is over here, mainly our nonmetals. And then the very bottom 2 rows are the F block. So how you can use this is as you are going down the periodic table, you know that you're adding on electrons. As you go across and down, you're adding an electron each time you move over one box. So you know where that electron goes by looking at this periodic table here. The electron right here, for example, the very first one, it's found on the first row. This is hydrogen, by the way. It's found on the very first row, so it's in the first energy level. That is the S block, so it is in the S orbital, and there's only 1. So there's 1 electron. How do I know there's only 1? It's just 1 box. If I kept going, reading it left to right, I would fill in electrons in those energy levels and orbitals as I go down. Now, I told you guys there are only a certain number of electrons that can go in each one, and you don't have to memorize that. That's because each block tells you how many electrons can go in that orbital. So for example, on the first energy level, you do need to take note that helium over here is actually part of the 1s orbital, and there's only 2 boxes there in that first energy level for the s orbital. And remember, an s orbital can only have 2 electrons in it. If you look at the p block, there are 1, 2, 3, 4, 5, 6 in the p block here, and recall that a p orbital can only have 6 electrons. Same thing is true for D and F. D can only have 10, you can count over, and then F can only have up to 14. So you can easily just look at the periodic table and see how many electrons can go in each orbital. Now you read this like a book, so you always start with hydrogen and read left to right, working your way down. So take note, in the second and third energy levels or rows, there is no D orbital. It goes straight from an S over to a P. Now whenever you get to the fourth energy level, it starts out with an S as always, but then before you can get over to the P, you will hit the first D orbital. And the D and the F orbitals are a little bit different, and I'll show you that on the next slide. But you'll fill in this orbital first and then move over to the 4P. So you just keep filling in as you go down, and based on where that electron is found on the periodic table, you can look at this and it'll tell you which orbital and which energy level it goes in. So here's the weird exception about the D and the F orbital. So remember, the row number tells you what energy level you're found on. So on the fourth row, we said that it goes to 4s, but then whenever you get to the D block, something happens. It actually shifts down one number. It's actually kind of behind. So instead of it being the 4D, it's actually the 3D. So you'll go from 4s, and then you'll come over to the 3D. You'll fill this in, and then when you get over to the P block over here, it's not going to be 3P, it's going to be 4P, because the S and the P block follow the rule of what row you're on. It tells you what energy level. Same thing is true for the F orbital. Recall that it's on the 6th row, it's just inserted right here. On the 6th row, you'll fill in the 6s orbital, and then before you fill in 5D, you're going to pop down, and the F orbital is actually 2 row numbers behind. So even though this is the 6th row, this is going to be 4F. You'll fill this in first, and then you'll come on right back up and fill in 5D, and then keep going on until you get to the 6P. So let's work out an example so this makes a little more sense. Okay, so an example of an electron configuration. There are 3 different ways that you can write an electron configuration. The easiest way is called longhand. So this is just where I tell you you start from the very beginning and you fill in the electrons as you move down the periodic table. The next one is called orbital diagram. This is where you have boxes that represent your orbitals. And so this is where you kind of just draw a picture to represent the electron configuration. And then the very last one is a noble gas notation. This is the way that, scientists that actually study chemistry, this is how they write electron configurations. This is upper level chemistry. And the reason that's upper level is because it's the shortest way. This is the way that scientists do it because, remember, we're lazy and we like to do things quick and efficiently. So we're going to look at all 3 different ways using the example of sulfur. So whenever you're given an electron configuration, the first thing that you do is you find where that element is on the periodic table. So if you look, sulfur has an atomic number of 16. And so let's go look and see where sulfur is on the periodic table before we do this. So recall that sulfur is the 16th element, so that means it is found right here in the P block. And so what we're going to do for longhand notation, remember you always start at the very beginning. Always start with the first element. So if you're going to start here, we're in the first row, and we're in the S block. So we're going to fill in the 1s orbital. And then as you keep going down, and we will stop whenever we reach sulfur. So we got to keep moving down to the second row. And this is the 2s orbital. It's on the second row, and it's in the S block. So we're going to fill that in first. And then the second row has a p orbital in it. So we need to come over here and fill in the 2p orbital with its 6 electrons. We haven't reached sulfur yet, so we're going to keep moving down to the third row. So this is the third energy level, and again, this is the S block. So we're going to fill that orbital up. Keep moving. We've almost reached sulfur. So we are going to finally fill in the very last orbital. This is 3p, third row, p block. And you only need to fill it in as many boxes as you go over. So that would be 1, 2, 3, and then yes, you do count that element. That would be 4. So let's write that out in longhand notation. Okay, so recall we said that we were first going to start with the 1s orbital. There are 2 boxes in the 1s, and there can be 2 electrons, so it's 1s2. Then we went down to the second energy level, to the 2s orbital. 2 boxes compose that orbital, so 2s2. So 2 electrons will go in the 1s, and 2 electrons will go in the 2s. Continuing on the second row, we go to the 2p, and there are 6 boxes, so 6 electrons that can fill in that orbital. Go down to the third row, the 3s will get 2 electrons. If you notice, yes, all the s orbitals can get 2 electrons. Then on the third row, we'll finally finish with 3p. Now remember, we only went over 4 boxes on the 3p, so that is where we're going to stop. Now that's longhand notation. If you want to do this in orbital diagram, every s orbital has 1 box. 1 box equals 2 electrons, so that means you would only need 1 box for every s orbital in electron configurations. The p orbital has 6 electrons, so that means that a p orbital needs to have 3 boxes. And if you keep going down, the d orbital can have 10, so the d orbital needs to be drawn with 5. F can have 14, so that means it needs 7 boxes. But we only have S's and P's in this configuration. So this very first one, we're going to draw a box to represent the 1s orbital, another box to represent 2s, 2p, it's a p orbital, so it's going to have 3, the s orbital for 3s, and then the very last orbital, which is 3p. So you draw the boxes and you label the orbitals underneath. Now how do you tell me how many electrons go in each of those orbitals? You're going to draw little arrows, and the reason that we draw arrows is because electrons always have a spin. Now you don't need to know why, that's upper level chemistry, but what you need to know is one will go spin up and one will spin down for those 2 electrons. The 2s also has 2 electrons, so one will go up and one will go down. Now the p orbital, 2p, is completely full, so you're going to put all 6, one going up, one going down in each box. Same thing for 3s, one going up and one going down. Now this 3p is not completely full, so we're not going to draw all 6 arrows. Now most people want to go ahead and draw, they want to put 1, 2, 3, 4. That would be incorrect. And the reason that is because of Hund's rule, so make a note to yourself. Hund's rule says that you have to put 1 in each box before you start pairing them up. So what we're going to do, we have 4. So I'm going to put 1, 2, 3. Now that I put 1 in each box, now I can start pairing them up and drawing my down arrow electrons. So the very last one is going to go in that first box there to make a 3p4. So take note of that Hund's rule. It only applies whenever you're filling in that very last orbital that's not completely full. Okay, so now let's do a noble gas notation. Now in order to do noble gas, you have to find the noble gas on the row before it and put that into a bracket, and then you're going to only write the remaining electron configuration after that. So in order to do noble gas notation, you're going to have to take another look at the periodic table. So let's go back to that very quickly. So recall that we said that sulfur was the 16th element, so it is on the third row. Now in order to do noble gas notation, you need to look at the row before it and look at the noble gas that is on that row. Remember, the noble gases are in the 18th group. They're the very last column here. So it's not going to be the noble gas that's on the same row as sulfur. It's going to be on the one right before it, which happens to be neon. So we're going to write neon in brackets, And then after neon, if you were going to continue on with the electron configuration, after neon, you would go all the way over down to the third row. You read it like a book. We finished with this line. We're going to come down to the next one. So the third row, you only need to fill in the electrons until you get up to sulfur. Remember, this is the short and easy way. Instead of writing the 1s2, 2s2, 2p6, instead of writing all of that, you just write neon in brackets and then only write whatever comes after it up until you get to that element. So the only thing that gets filled is the 3s, and then the very last one is that 3p with only 4 electrons. So let's go write that down to finish this example. So to finish this problem off, we're doing noble gas notation. So the noble gas that comes in the row before sulfur is neon. So instead of writing out the 1s2, 2s2, 2p6, instead of writing all that out, you just put neon in a bracket. This is the electron configuration for neon. So the only thing that you have to write after neon is whatever gets filled up after it. So that would be the 3s2, and then the very last one was 3p4. So that's all 3 different types of electron configurations, which you will work out tomorrow in class. So if you have any questions, let me know before we start working at our examples.